Let's see if we can develop a model for the elevation of the boiling point of a mixture. This will allow us to predict the boiling point of a mixture. If we have a dilute solution so that the solvent is nearly pure, the solvent can be approximated using Raoult's law, or we are in the ideal solution limit where the mole fraction is equal to the activity. Therefore, I can write that the chemical potential of the gas is equal to the chemical potential of the solvent in the solution, which I can write as the chemical potential of the pure solvent plus RT times the natural log of the mole fraction of the solvent in solution. Since I really want to know how the temperature changes when I change the mole fraction of the solvent in solution, I really want to know the partial derivative of the mole fraction with respect to temperature. It will be easier to look at the partial derivative of the natural log of the mole fraction with respect to temperature, and this will give us basically the same information. So to find this derivative, I need to solve my equation for the chemical potential for the natural log of the mole fraction. When I do this, the natural log of the mole fraction of the solvent in solution is equal to 1 over R times the mole fraction in the gas phase divided by temperature minus the chemical potential of the pure solvent divided by temperature. Using the product rule to take the derivative with respect to temperature gives me 1 over R times the quantity 1 over T times the derivative of the chemical potential in the gas phase with respect to temperature minus the chemical potential in the gas phase divided by T squared minus quantity 1 over T times the derivative of the chemical potential of the pure solvent with respect to temperature minus the chemical potential of the pure solvent divided by T squared. Recall that the derivative of the chemical potential with respect to temperature is equal to minus the molar entropy. Remember also that the chemical potential of a pure substance is equal to the molar Gibbs free energy of that substance. Making these substitutions, I can write that the derivative of the natural log of the mole fraction with respect to temperature at constant pressure is equal to 1 over R times the quantity molar Gibbs free energy of the pure solvent minus the molar Gibbs free energy of the gas divided by T squared plus the molar entropy of the pure solvent minus the molar entropy of the gas divided by T. The vaporization process is liquid in equilibrium with the gas, and so the delta G of vaporization per mole is equal to the molar Gibbs free energy of the gas minus the molar Gibbs free energy of the pure liquid. Likewise, the change in entropy for vaporization is equal to the molar entropy of the gas minus the molar entropy of the pure liquid. Making these substitutions, we can write that our derivative of the natural log of the mole fraction with respect to temperature is equal to minus 1 over R times the change in Gibbs free energy upon vaporization of the pure solvent divided by T squared plus delta S for vaporization of the pure solvent divided by T. And now because delta G is equal to delta H minus T delta S, I can write that our derivative is equal to minus the delta H of vaporization divided by R T squared. Now that we have our differential expression, all that remains is to separate variables and integrate. So if I separate variables, I have d natural log of x is equal to minus delta H of vaporization for the pure substance over R dt over T squared. I'm going to integrate from the pure substance, x equals 1, to any other composition because I know the boiling point of the pure substance. And so my integral on the right-hand side is delta H of vaporization over R dt over T squared from the normal boiling point of the pure substance to the boiling point of my mixture. Integrating both sides gives me that the natural log of x is equal to delta H of vaporization for my pure solvent divided by R times 1 over the boiling point of my mixture minus 1 over the boiling point, normal boiling point for my pure solvent. At this point, we have this in terms of the mole fraction of the solvent. We more commonly describe the composition of a solution by using the mole fraction of the solute. But the mole fraction of the solvent and the solute are related because they have to add up to 1. So if I make that substitution, I have natural log of 1 minus x of the solute is equal to delta H of vaporization over R times 1 over the boiling point of my mixture minus 1 over the boiling point of my pure solvent. If our solution is dilute, then x solute is less than 1, and we can approximate the natural log of 1 minus a small number as equal to the opposite of that small number. So if I make this substitution, the mole fraction of my solute is equal to minus delta H of vaporization over R times the quantity 1 over the boiling point of my mixture minus 1 over the boiling point of my pure substance. At this point, it pays to take stock of where we are. What we want is an expression for how the boiling point changes when I add a solute. So what I really want to know is how much larger is the boiling point of my mixture compared to my pure solution, my pure solvent. That is what we call the difference in the boiling point. Notice that the boiling point of the mixture is always larger than the boiling point of the pure solvent, and so if I take the boiling point of the mixture and subtract the boiling point of the pure solvent, this will be a positive number. So this is the thing that I'm after, and I want to know how that is a function of the mole fraction of my solute. What I have is the difference of the reciprocals, not the difference of the temperatures themselves. So let's get a common denominator and see where that leads us. Getting a common denominator for my fraction, I end up with the difference in boiling points up here and the product of the two boiling points down below. If we make the approximation that T boiling is not too terribly much different than the boiling point of the pure solvent, then we can say that the product of the boiling point of the solution times the boiling point of the pure solvent is approximately equal to the boiling point of the pure solvent squared. Notice that our difference is the opposite of the difference that we want, but we have a minus sign that multiplies the entire equation, and so we can finally write that x of the solute is equal to delta H of vaporization for the solvent divided by R times the boiling point of the pure solvent squared times delta T boiling. Remember that delta T boiling is equal to the boiling point of the solution minus the boiling point of the pure solvent. And now the last step is to rearrange this equation so that we have an equation for the difference in boiling point between the solution and the pure solvent, and that gives us R times the boiling point of the pure solvent squared divided by the delta H of vaporization of the pure solvent times the mole fraction of the solute. Notice that all of these terms here are constant, and they depend only on the solvent. They're only solvent properties. So it doesn't matter what your solute is. The combination of these factors will only depend on what your solvent is. So all solutes will elevate the boiling point of a given solvent by the same amount, regardless of what they are. This combination of factors of solvent properties is called the ubulistic constant for the solvent. These are tabulated in tables.